Hi, I'm Aaron Sampson, and in this course I'll cover the OSI layers and examine where various devices, services, and protocols reside. I will also cover the well-known ports and their associated numbers. Alright, in this presentation we will take a look at TCP, or the Transmission Control Protocol, which establishes and maintains network communication for applications to exchange data. Now, it works in conjunction with the Internet Protocol, or IP, and of course creates the name we are all familiar with, TCP/IP. So as mentioned, it defines how computers send packets of data to each other on a network. Now that's a fairly loose description, but in fact you can see the full definition in what's known as RFC 793. Now RFC stands for Request for Comment, and this is effectively how protocols are developed. Nobody owns TCP/IP. It really is developed by the community, if you will, and an RFC is when somebody says, I think the protocol should do this or should have this feature. And anyone can submit any kind of suggestion to an RFC. That is reviewed, and if accepted, it is ultimately worked in to the definition of the protocol. So they are continually evolving. So you could just do an internet search for RFC 793, and you would see, in essence, the development of the protocol. Now, one of the key characteristics of TCP is the fact that it is connection-oriented. This means it establishes and maintains a connection until the applications are finished exchanging data. Now, that might seem like a fairly obvious approach. Of course, it establishes a connection and maintains it. And you might equate that to a phone call. I have to pick up the phone, dial a number, somebody else has to answer, then we talk, and then when we're finished, we hang up. That closes the connection. And even if we aren't speaking for a few seconds at any point in time, the connection is still there. But we will, in fact, see certain types of applications and protocols that really don't use that approach. Now, we'll clarify that a little bit later on. But when it comes to applications that use TCP, they do maintain this connection. So the responsibilities of the protocol are to provide for guaranteed delivery of packets, also to handle packet retransmission in the event of an error, and it does this through the use of acknowledgements. So when a packet is received on the other side, it says, I received that, and you can therefore be assured that your transmission has been received. And you might equate that to sending a package through a courier. Oftentimes, you want the recipient to sign to acknowledge that they received it, so you know it has arrived safely. TCP does the same thing. When a packet is sent, it waits for the other side to acknowledge the receipt of that packet, at which point the originating application will send another packet. And it will wait for an acknowledgement from the other side for that one. And it will keep doing that over and over again. And if an acknowledgement does not arrive, then it knows there was a problem and it retransmits the packet. So this is how you get that guaranteed delivery. If it was not received, I'll resend it. So it will ultimately always arrive when using TCP. Now, in terms of the architecture, we will certainly take a more detailed look at both of these models, the TCP/IP model and the OSI model. But they represent a means to develop protocols and applications and hardware that is independent of other components. In other words, if I'm an application developer, I really don't want to worry about developing network interfaces. That's not really my job, if you will. So the layered structure allows developers to focus in on just their own little portion of an overall application or network protocol or piece of hardware. So again, we'll clarify that a little bit more later on, but you do see in both models there is a transport layer. And as mentioned with the courier analogy, you have to move a package with a courier from one place to another. So it is the transport layer that is responsible for moving packets from one place to another in terms of network communications. And TCP resides in that layer. So that's its job, to just get the packets from point A to point B. It doesn't particularly care what the application is, nor does it really care, for example, what the physical network interface is. That's not its job. It is simply responsible for accepting a packet, sending it on its way to the other side, and then waiting for that acknowledgement to come back so it can start all over again and just keep doing that. So with this very focused task, it can provide those guaranteed communication services. Now, the slight downside is that it can be a little bit slow compared to some other methods because it sends, it waits for the acknowledgement. If the acknowledgement doesn't come, it sends again. So the overall communication can be a little bit slower when using TCP, but it is more reliable. So those are the key characteristics of communications when using the TCP protocol. Now, in this presentation, we'll take a look at the Internet Protocol, or IP, which is also used in the delivery of data from one computer to another over the Internet for common applications such as email and web pages. But it does not operate on its own. It is used in conjunction with TCP to, again, form the familiar name TCP/IP. But IP specifies the format of the packets and, perhaps most importantly, the addressing scheme. Now, we will certainly clarify that in a moment, but in terms of some of the characteristics of the protocol itself, IP is connectionless, meaning there is no continuing connection between the hosts communicating together. Now, earlier we talked about TCP and how it does establish and maintain a connection. So it's not that it isn't there, it's just that IP doesn't really care about it. That's not its job. TCP maintains and establishes the connection. IP says, great, but I don't need to use that. As far as it's concerned, packets are treated as an independent unit of data with no relation to any other unit of data. And in fact, packets can be sent out and not necessarily travel the same path through the internet to arrive at their destination. And if that's the case, they will then be assembled in the correct order because of the TCP protocol. Again, not IP. So let me go back to the analogy of sending a package using a courier. TCP's job was to ensure the package arrives safely. You can do that by requesting the signature. That says the recipient got the package safely. Great. But there is a pretty important component missing. What was the address? That is the job of IP. So that's what I mentioned when I talked about the addressing scheme. TCP says, great, here's your signature. IP says, where does it have to go in the first place? So let's assume you have two packages. It doesn't really matter if those two packages go on different trucks or different planes or travel different highways or different routes, as long as they arrive at the same destination. So again, IP just doesn't care about that connection and the signature, the acknowledgement. It just says get it to that address by whatever means is hopefully most efficient, but it does not have to be the same every time. So that's what it means when it says it's an independent unit of data. All I have to do is get this package to the correct address, and my job is done. So the IP protocol operates at a lower layer than does TCP You can see it's at the network layer of the OSI model. And again, there are other protocols there, but IP handles that routing, the addressing, ensuring it ultimately arrives at the correct location. So it doesn't need the connection. It's not concerned with the acknowledgements that happen up in the transport layer. That's TCP's job. So the two of them certainly perform most important functions, if you will, of ensuring it gets from point A to point B in the correct manner. Now, with respect to its address format, the first one that we'll take a look at here is IP version 4. This is probably still the most common by far, but there is a newer one we'll see in a moment. So this is the 4th version of the IP protocol, and it is made up of 32 bits or 4 bytes. And with this format, you can see there are binary values at the bottom of the graphic, just ones and zeros, in groups of 8. And then that is converted into what we call a decimal value. And we will see how all this is done later on. But with 32 bits of 2 possible values, 1 and 0, it gives you 2 to the power of 32 possible addresses, which is approximately 4 billion, which might seem like a lot, but in fact, that is becoming limited with the number of devices that are on the internet these days. Hence, IP version 6 has come out and is the successor to IP version 4. This has a 128-bit address space, which supports 2 to the power of 128 total addresses, which is just an enormously large number. You can see there approximately 3.4 times 10 to the power of 38, or 340 trillion addresses. That is, for all intents and purposes, inexhaustible. That is just unbelievably huge in terms of the total address space. Now, you can see it looks quite different. It is still binary at its core, but hexadecimal characters are used to represent it. And the format that you see here can be condensed a little bit by suppressing the zeros. So if you see a leading 0 in a group, then it can simply just not be shown. So the 0 DB8 can be represented as just DB8. The protocol knows the 0 is there. It says, wait, there's only 3 characters, there's supposed to be 4, therefore the first character is a missing 0. If there are 2 of them, you can suppress both. And if you have subsequent groups of all zeros, they can be represented by simply closing the colons together. And again, the protocol knows that if those characters aren't being displayed, they're just all zeros. So it makes it a little bit simpler to us, of course, who simply have to look at the address and read it. So suppressing the zeros makes it a bit simpler. Now, in terms of implementation, most operating systems these days support both, and in most of the later Windows operating systems, IP version 6 is the default, but it doesn't mean that you can't just disable it if you want to. You don't have to use it. You can use 4 or 6, but 6 is certainly becoming more common. It was designed for newer types of communications, specifically things like voice over IP and video conferencing. It's a little better at handling those types of applications, but its address scheme is certainly more complicated. So version 4 is, I would say, probably much more common still in most environments, but it is up and coming, if you will, and will certainly grow in terms of its implementation as things move along. But as of the time of this recording, both protocols are in place. They are there. Either can be used. Both can be used. It really is up to you. And of course, depending on which applications you implement most frequently, you might be better suited for one protocol or the other. But again, it really is your choice. So ultimately, IP responsible for that address format and moving the packets to the correct addresses through the internet using whichever route is necessary to get it from point A to point B. But again, not concerned with things like acknowledgements. That's TCP's job. So IP just stamp that address on there and send it on its way. Now, in this presentation, we'll take a look at the User Datagram Protocol, or UDP, and this is often implemented as an alternative communications protocol to TCP. And I say alternative because you do have a choice. It depends on the application and the circumstances with respect to which transport protocol you choose. Now, I'll clarify that in a moment, but UDP is primarily used for communications that favor low latency, or quite simply speed, and also those that can tolerate some data loss. And you might think, well, when is it okay to lose data? But there are situations where it's not that big a deal. Now, it still runs on top of IP. In other words, it is a transport layer protocol similar to TCP, so IP is still required for addressing and routing. So the choice then really is which transport protocol to use. So, looking at some of the use cases, UDP is the ideal protocol for network applications such as gaming, video communication, voice communication, or any data that can suffer some data loss without affecting the overall quality, or where you can rely on the application itself to be responsible for retransmitting lost packets and arranging received packets. You can work that into the application if you want to. It does not have to be the job of the transport protocol. So, again, to clarify all of that, let's recap TCP. It implements communications by establishing a connection and then using acknowledgments to provide that guaranteed, reliable delivery. That's certainly good, but it comes at a cost. It is slower. So you favor the reliability, but you sacrifice the speed. UDP is the exact opposite. It does not implement a connection, nor does it use acknowledgments. So where I equated TCP to a phone call, where you have to dial a number and somebody has to pick up, there's your connection, UDP would be more like sticking your head out the window and just screaming at the people below. You, in essence, hope that they will listen to you, but you really don't know if they are. But you are still sending the information out. So again, in terms of things like video communication or voice communication, imagine you are watching a YouTube video. In this case, you want it to come down as fast as possible. And if a little bit of it is garbled, or if you miss something, it's not critical because you can just load the video again. It's not going anywhere. It's still there on the server. So it is, in that case, acceptable to lose a little bit of data. In most cases, you'll just be like, well, that was no big deal. I'm just going to let it play. The same goes for voice communications. Even if you are speaking to someone using voice over IP, if something got garbled and you missed it, well, you could just ask them to repeat it. So in those cases, data loss is acceptable to a degree. But ultimately, it's the speed. I want the performance of the application to be as high as possible. I am not as concerned with the reliability. Therefore, UDP is the better choice. So as mentioned, in terms of the OSI model, it does operate at the same layer as TCP. They are both transport protocols, but they handle that transport differently. That's basically the choice between the two. So when it comes to the application, UDP works in conjunction with the higher level protocols, just like TCP does. But again, it's the certain type of transmission that you want that determines the transport protocol that is most appropriate. So we see the first example, Trivial File Transfer Protocol, or TFTP. Well, this uses UDP as its transport protocol. It favors speed. FTP, all by itself, uses TCP as its transport protocol. It favors reliability. Real-Time Streaming Protocol, or RTSP, Simple Network Protocol, SNP, and even Domain Name System Lookups, DNS, all actually favor UDP as the transport protocol because they aren't as concerned with the reliability. If something fails, it's usually not critical. If it is somewhat critical, we can just try again. So, as an application developer, you can design your applications and, in essence, decide for yourself what's more important, speed and performance or reliability and guaranteed communications. If you like speed, you'll want UDP. If you like reliability, you'll want TCP, and that is your choice. Now, in this presentation, we'll take a look at the Internet Control Message Protocol, or ICMP, and it's responsible for providing error reporting services. It generates error messages when there are problems delivering IP packets, and it creates and sends messages to the source IP address, indicating any issues with the router, the host, or the service. Now, any IP network device can send, receive, or process ICMP messages. It's a built-in functionality, if you will. And it is, in fact, one of the main protocols in the overall Internet Protocol suite. But it's not a transport protocol. It does not serve the functions of maintaining connections or acknowledgements or anything along those lines. But it certainly is commonly used in diagnostics and troubleshooting. If you have ever issued a ping or a traceroute command, they exclusively use ICMP in terms of getting the status back. Ping more or less just says, "Are you alive?" And traceroute quite literally traces the route a packet takes from point A to point B. So they both rely on ICMP. So the messages themselves are transmitted as datagrams in two broad categories: error reporting and query messages. So the error reporting is, of course, something went wrong. So if there is a problem, it is the responsibility of ICMP to report that error. Query, as mentioned just a moment ago, is like the ping command. It is effectively, what is your status? Are you alive? Are you able to receive? So one of the very first troubleshooting techniques when any kind of communication fails is, can you ping that system? So that's sending out the query. Are you there? Can you hear me? So those are the two basic categories of ICMP messages. And again, a lot of different applications will use ICMP, but its primary function is really just to report those errors and or to query the status. It doesn't really do anything to correct them. It's just so that you can be made aware of the problems so that they can then be addressed. In this presentation, we'll take a look at the connection-oriented protocol, which is used by endpoint devices to transmit data, although perhaps not directly. Now, I'll clarify what that means in a moment, but it's more so of a preliminary protocol used to establish end-to-end connections. So, if you think about any two people having a conversation, as long as they both speak the same language, then of course they can both be understood. So in terms of network communications, we tend to think of the protocols as the language. That is ultimately how you communicate. But again, for two people who know the same language, there are some intrinsic rules that both parties know in order to communicate effectively. In other words, again, going back to the conversation, if I'm speaking to someone, I know that I should not speak when they are speaking. In other words, I should let that person speak, listen, then respond. And of course, the person on the other side should take their turn listening. And of course, that's how you implement a normal communication. You also know that you really shouldn't speak too quickly, or you shouldn't use terms that maybe aren't familiar to the other person. So there are several rules, again, that are really just implied in this example, but we know those rules. So this is more so the connection-oriented protocol. It is not really concerned with the language or the direct communication, but rather setting up the rules of communication. So it is referred to As the reliable service network, it guarantees data will arrive in proper sequence. And an example of a connection-oriented protocol is TCP, which we did discuss earlier. But that's an example of one of the rules, making sure it arrives in the proper sequence and that it is guaranteed to arrive. And again, TCP implements that through the use of acknowledgements. So it's not so much a matter of the direct communication, but rather how the communication will occur. So in terms of the benefits for a connection-oriented protocol, it is less error-prone, it's more reliable, and data arrives in the same order. Now, with respect to that order, it is not 100% guaranteed that everything will actually arrive on the network interface in the correct order, but it is ultimately reassembled in the correct order. So as far as the application is concerned, it doesn't care if one packet arrived ahead of another in the wrong order. As long as they are ultimately assembled correctly, that's the main thing. So again, the TCP protocol, which is connection-oriented, in essence, provides these benefits. It can inform the sender if there is an error. It can say, that data is corrupted, please resend. It will be resent. And if anything is out of order, it will ultimately be reassembled in the correct order. So it is less error-prone and more reliable, but that does come at a bit of a cost. It is generally a slower protocol. If you have to resend lost packets, it is going to take more time. If they are arriving entirely out of sequence and it has to then be resequenced, that takes a bit of time. So you sacrifice the speed for the reliability, but depending on what the application is and the type of communication you want, then these generally provide the benefits that are necessary. So when it's an application that really does not have to be all that fast, and we really want it to be safe and secure and reliable, then connection-oriented protocols are often chosen. So ultimately, again, it's not really handling the communication itself, but setting up the rules of communication, and TCP is a good example of a connection-oriented protocol. Earlier, we talked about connection-oriented protocols. Now, in this presentation, we'll take a look at the connection-less protocols. But before getting to that, I just want to talk about the term connection. Obviously, if two systems are communicating with each other at a fundamental level, or perhaps a physical level, if you will, there is a connection. Information is flowing between those two systems. So the term connection in that connotation doesn't really refer to that physical connection. It is more so how the connection is set up. So if we look at the connection-less protocols, we see communication sent between the two network endpoints without any prior arrangement. That is the distinction between the connection-less and the connection-oriented. If we quickly go back to the connection-oriented, there is a negotiation, if you will. There are some rules that are set up and defined. One system will say, I have data to transmit. Are you ready to receive? The other end will say, yes, I am ready. And then they'll negotiate some other characteristics such as the rate of transmission and how to re-request any data that might have been lost. So those rules represent the connection in this implementation. So with connection-less protocols, we just don't see those rules. Any given device will send the message prior to ensuring the other device on the other end is even ready to receive it. So it just doesn't concern itself with, are you ready? What are the rules? What do we do in the event of error? It just send. So this, in fact, is the case in most open internet transmissions. And again, a common example of that is video streaming. It just does not concern itself with, is the other end ready? It's just going to send it. Now, certain protocols can still allow for error correction. In other words, retransmission can be requested if necessary, but it typically is not the job of the connectionless protocol. It's usually one of the higher level protocols that will handle that retransmission. So some of the supported connectionless protocols include IP, UDP, the counterpart to TCP, ICMP, and IPX, and there are others, of course, but UDP is certainly one of the most common examples of a connectionless protocol. Now, it still operates at the same layer as TCP. They are both transport protocols. So again, it's still moving the data from one place to another. It is simply the fact that those rules are not really implemented in the connectionless protocol. That is the job of a connection-oriented protocol, such as TCP, but UDP says, no, I don't want to bother with that because, again, of course, the drawback of the connection-oriented protocol is speed. They are not as fast. They are more reliable, so that's great, but they aren't as fast. If you don't concern yourself with all of those rules, you can just send the data a lot faster. So in terms of the features, there is no reliability built into connectionless protocols. There are no error messages. So in this example, we see not all data was sent. There is no request to resend. But again, higher level protocols can be implemented to address those problems if necessary. And these are often referred to as stateless communications. Since there is no negotiation, no setup, no set rules, then they typically call this a stateless connection. Those that do implement those rules effectively refer to the connection to be in a certain state. So connection-oriented protocols are stateful. Connection-less are stateless. Now, in terms of some of the types of transmissions, there are three basic types: the unicast, the broadcast, and the multicast. Now, we don't see the unicast here because typically unicast transmissions generally use connection-oriented protocols. They don't necessarily have to, but the unicast is one-to-one. The broadcast is one to everyone, and the multicast is one to many or several. So if you have a single system on a network that needs to communicate with every other host on that network, it will use a broadcast. It sends the packet simultaneously to every other system. So if it needed to negotiate those rules with every other system, it would simply take far too long. And the same goes for multicast. Now, you never really know how many systems are in a multicast group. Somebody sets up the group and says this particular host belongs to a specific multicast group. So you can create several smaller groups from the entire network, and then you can send a packet to just the group. But the same thing applies. You don't want to spend time setting up those rules of communication with all of the other systems within the group. It would just take too long. So broadcasts and multicasts typically will implement connectionless protocols when transmitting because, again, it quite simply is faster. So ultimately, there is a fairly basic consideration. If you favor reliability, you would want to implement a connection-oriented protocol. If you favor speed, you would want to implement a connection-less protocol.
Let's take a moment to look at the well-known ports that are used by TCP and UDP. Remember, these are layer 4 protocols, so they do use port numbers to create their sockets. Now, a well-known port is basically a port below number 1024. We also call these the service ports because these are used to identify the specific type of service that's being requested from the client system. So, for example, in the IP header, this would be the destination port or the service port. The source port or the originating port will typically be some ephemeral port number that's chosen by the client somewhere well above 1024. Remember, TCP and UDP ports, in the header, this is a 16-bit field, so we have 65,534 possible ports for TCP, and then we have another 65,000 plus for UDP. One of the most common would be the File Transfer Protocol service ports 20 and 21. Now 20 is the port we use for data, and 21 is the one we use for basically control packets or control segments that are sent. So FTP actually uses a couple of different ports. Secure Shell will use port 22, and Secure Shell is a very important protocol. We want to use Secure Shell version 2, which uses the Diffie-Hellman protocol to generate shared secret keying material. It's the most secure, but we can also use port 22 for the secure file transfer protocol. That would be basically Secure Shell over FTP. So it's FTP also using SSH together. So port 22, very common port. Another common port is Telnet. We don't use Telnet as much anymore. We'd like to use port 22 in Secure Shell whenever possible. Telnet, of course, is an unsecure protocol. It sends the information in clear text. So typically we're going to replace Telnet on port 23 with Secure Shell on port 22. SMTP is the protocol that's used to send information between message transfer agents. Your email program, this is port 25. 53 is very popular. That's the DNS. As a matter of fact, Amazon Web Services has a service called Route 53, and it is basically their DNS service in the cloud. And so to help remember that, remember Route 53, and that's the domain name service. Now, 53 is used by DNS for TCP 53 and UDP 53. So sometimes protocols will use both TCP and UDP. And this is one of those cases because if it's a DNS query, that's going to be done with UDP 53. If it's, say, transferring some database from one DNS server to another, that would be using TCP port 53. DHCP is the Dynamic Host Configuration Protocol that is going to lease out IP addresses and other option information to those network clients. The DHCP server operates on UDP port 67, and the DHCP client operates on UDP port 68. 69 is the Trivial File Transfer Protocol. This is going to be using UDP, and it's UDP 69. We often use TFTP to download configuration files for routers and switches and firewalls. Probably the most popular port out there is TCP port 80, and that's for HTTP, Hypertext Transfer Protocol. Even though we're starting to see port 80 used a lot less and being replaced with the port for HTTPS, which we'll see here in a second. Another common protocol on the internet when you download email is POP, Post Office Protocol. This is going to be TCP 110. 123 is the Network Time Protocol. That can also be UDP or TCP, but most commonly we're using UDP port 123. 143 is IMAP, Interactive Mail Access Protocol. 161 is SNMP, very popular network management protocol, simple network management protocol. Another very common protocol is the Lightweight Directory Access Protocol, LDAP, used to access configuration items in a directory like Active Directory. A lot of organizations today will block port 389 and actually use the SSL TLS version of LDAP, and that's going to use port 636. If you use the secure version of HTTP, instead of using port 80, we're going to use port 443, and this is very common for SSL TLS. 445 is used in a Microsoft environment. That's going to be Server Message Block, Microsoft SMB, using port 445. And of course, there's our 636 I just mentioned. That's the Lightweight Directory Access Protocol over SSL, and technically you're using TLS, Transport Layer Security 1.1 or 1.2. We call that LDAP-S, and that's port 636. H323 is basically an ITU recommended protocol that's used for audio-visual communication sessions on our TCP-based network. This particular standard, running on port 1720, is going to deal with all the call signaling and control, multimedia transport and control, and bandwidth control for point-to-point and multi-point conferencing. 3389 is the Remote Desktop Protocol. This is a very common protocol used in Microsoft organizations to get remote access to do management of systems, troubleshooting, tech support, and other purposes. In the voice over IP realm, a very popular protocol is Session Initiation Protocol, or SIP, and this is going to operate on port 5060 and 5061. Now that pretty much does it for the ports and services that are well known that you need to be aware of out there. But keep in mind that more often than not, what we're seeing is that clients and services are actually getting off the well-known ports and using other ephemeral ports. And as long as the client and the server agree, then they can have communication. So the well-known ports are also well-known to hackers and crackers and attackers. And so they're often the most commonly vulnerable ports in your network enterprise.
All right, based on what we've covered so far, it is time for a short exercise where we will ask you to recognize when to use port 80, then to describe the service that uses port 20, then to determine which port is used to send email, and finally to determine which port is used for secure internet transactions. So what we'd like you to do is take a few minutes, pause the video, jot down some responses, and then we'll come back to see a solution. So we'll see you in a few minutes. All right, so our first task was to recognize when to use port 80. This is for websites. The Hypertext Transfer Protocol, or HTTP, uses port 80 by default. So if you want to host a new website, it would be accessible through port 80. Then we asked to describe the service that uses port 20. This is FTP, the File Transfer Protocol. This is often used when copying files from a local system up to a web server. So if, for example, your site is hosted somewhere else other than where you are, you would develop the site locally and then simply upload those files. That's just a common use of FTP. Then we asked to determine which port is used to send email. This is port 25. The Simple Mail Transfer Protocol uses port 25 to send email by default. And finally, we asked which port is used for secure internet transactions. This is port 443, the secured implementation of HTTP, or HTTPS, uses port 443 by default. So hopefully you made out okay with those exercises, and if so, we are ready to move on.
Now, in this presentation, we will introduce the OSI model. That stands for Open Systems Interconnect. This is an architectural approach to developing network communications. You can see that there are 7 layers, and these divide up the tasks so that each layer is responsible for only a subcomponent of the overall communication process. And this helps to facilitate consistency when developing new applications, new protocols, or new devices. So why does it even exist at all? Well, imagine you're a company, and in fact the only company in the entire world that developed anything and everything to do with computing. If that was the case, you'd certainly divide up your company into departments, and you'd assign each department a special area of focus so that your application developers just don't have to concern themselves with the department that makes physical cabling and network adapters, hardware, for example, because if the application developers had to take that into account, then they would have to develop one version of the application for one type of hardware, and then another version of the application for a different type of hardware or a different type of network media. So clearly, we don't want to have to do any of that. As an application developer, all I want to do is develop my application. I don't want to concern myself with anything in the lower layers, the network protocols, the physical hardware. I simply want to focus on the application. So that is really the overall approach. Now, clearly, we have any number of companies that are developing these things, any number of individuals, all kinds of different types of applications, different protocols, different types of hardware that all have to be able to ultimately communicate with each other. So by focusing your efforts on 1 or 2 or 3 layers, then you don't have to concern yourself with the other layers. And in terms of communication, any one layer is in fact only aware of the layer above it. So the application layer for example, has really only the user above it, and so it only needs to be aware of the presentation layer. Similarly, the physical, there's nothing below it, so it only needs to be aware of the data link layer. But some of the ones in the middle, such as the transport layer, need to be able to interoperate with the session layer and with the network layer. But still, nothing beyond that. So if I'm developing a protocol at the transport layer, my world is the session layer, the transport layer, and the network layer, and that's it. Now, we'll talk about what each layer does in the upcoming presentations, but for the time being, suffice to say that as you begin your communications, the packet begins at the top. The application layer on the sending side, and then travels down the stack to the bottom. And each layer does whatever it's supposed to do to that packet to get it into a format to be transferred across the physical wire. So once it's ready to go, it is then transmitted and accepted by the bottom physical layer on the receiving side. So it travels down the stack and across the wire, and then the physical on the other side picks it up, if you will. And then the packet travels up the stack on the receiving side and ultimately, arriving at the top, the application layer of the recipient. So this is what it looks like. We see the sender on the left, and again, imagine the sender is me and I'm sending you an email. So I'm using some kind of application to type my message, and the application layer accepts that and sends it down the stack. Each layer does what it needs to do to the packet. It travels across the wire. You, as the recipient, will see that on the wire, and you will pick it up. Now it's at your physical layer and it sends it up the stack. And whatever was done to it on the sending side is, for lack of a better word, undone on the recipient side. So that by the time your application receives that packet, it's the exact same data that I sent in the first place. Now, to give you one very quick example of what that looks like, the presentation layer is responsible for things like compression and encryption. So, and again, we'll talk about this later, but if I was sending you an email and I wanted it to be safe, I might digitally sign that email and encrypt it. It's the presentation layer responsible for applying the encryption, sends it down the stack. You receive it, and it's the presentation layer on your side that's responsible for decrypting it and presenting you with the data that I sent originally, so that it's in a readable format so you can understand it. If the presentation layer on your side did not do its job, you'd be presented with encrypted data that made no sense. So that's basically this virtual communication between layers. The presentation layer on my side interoperates with the presentation layer on your side. And again, that happens at every layer. There's a communication between adjacent protocols. Each layer does something to the packet, which is then supposed to be handed by the corresponding layer on the recipient side. So again, that's what it means when it says virtual communication between layers. Any given layer is only concerned with what was done to it on the sending side of the same layer, not really anything else. So again, as a developer, it's basically up to you to decide where you want to kind of work within that stack, if you will. You generally don't find people that can develop for the entire stack. I'm not saying it's impossible by any means. You may be a very skilled developer and you can work in all of them, but you typically tend to specialize. If I'm going to be an application developer, I'm just not going to concern myself with building new routers and switches and things along those lines that operate down at lower layers. And conversely, if I'm concerned with developing hardware, I'm not going to concern myself with developing applications. So again, this allows for that consistency. Everybody follows the same approach, the same plan. And we can rest assured that if we do follow this approach, then everything should be ultimately compatible in terms of supporting network communications. The term for the information being communicated at common levels of the OSI model is a PDU, or Protocol Data Unit. The application's information presented at layers 5 through 7 is called data. The transport layer headers and data that it contains are called segments. And that's because they are used to divide up the original data into network bite-sized pieces. At the network layer, we refer to the header as a packet, and the protocol data unit for the data link layer is referred to as a frame, because the data has a header on one end and a trailer on the other, meaning the data has been framed. To put it all together, HTTP data is placed within TCP segments, which are addressed with IP packets, which are then put on the wire using Ethernet frames. Now, don't confuse PDU with MTU, or maximum transmission unit. This is the bite-sized piece that a layer 2 network can support. Ethernet, for example, commonly supports carrying 1,500 bytes of data in its frame. If a frame is received on one interface of a router but must exit another interface using a smaller MTU, the packet will be fragmented at layer 3 before retransmission. In this example, we could see that data moving from one system to another would not have any problems because this is all under the MTU. So the original payload of 3,600 bytes will be divided into 1,500 byte chunks and sent on its way and get received on the other end. But if that same file was sent the other way, when it reaches a router that accepts 9,000 on one side but only 1,500 on the other, we will see fragmentation occur in order to make this particular block of data acceptable for the network devices that are in that network. The challenge with fragmentation is that there's no guarantee that the data will get there. So if you lose one fragment, you'll have to resend all the fragments that made up the original segment.
Now, let's begin taking a closer look at the OSI model layer by layer. And in this presentation, we'll start with, of course, layer 1, or the physical layer. This is responsible for transmission of digital data bits from the source device to the destination device over the physical network communications media. So, as its name implies, at this layer, we find physical devices. Hardware. So there are 4 main functions happening here, and it begins with the definition of hardware specifications, including the details for cables, connectors, network interface cards, repeaters, hubs. So what you might notice about the devices at this layer is that there is very little, if any, programming going on. You don't configure a cable. You don't go in and program a connector. You basically just physically set them up and they work. So really no configuration. Nothing has to be accessed in terms of an interface to get to it. It's just there. It's ready to go. So those are the types of components that we find at the physical layer. Now, the network interface card is a little bit of an exception. We know that there is some programming that's built into a network interface card, and of course it has a driver for the operating system. But from the perspective of configuring a network, you just insert the network interface card into the computer, or of course it's already built in. And again, it works. It's already set to do what it needs to do. And it is, after all, a hardware component. So it does correctly reside at the physical layer. Then we see encoding and signaling. This is used to transform data from bits, ones and zeros, into electrical signals. Those signals are then sent over the network. Then we see topology and physical network design. Then we see the data transmission itself. This, of course, handles the sending and receiving of the data depending on the type of physical media. Whether it's wired or wireless, for example, it needs to know what type of network. Then we see data transmission, which is actually sending and receiving the data. And of course, for the particular type of network. For example, is it wired or wireless? Because, of course, there are different methods for each one. Then we see topology and physical network design. This considers things such as LAN, local area networks, versus WAN, wide area networks. Again, there are different considerations, different methods for sending the data when you have those different types of topologies. So, another component that you'll also find at the physical layer is the bit rate control, which is the transmission rate, or the number of bits per second. so that you don't overwhelm the physical media by trying to send too much. So again, we see the ones and zeros that come down from the data link layer, which is layer 2. Then at the physical layer, they need to be converted into electrical signals that can travel the physical transmission medium. They are then received on the other side by the physical layer. They're converted from those electrical impulses back into ones and zeros and sent up to the data link layer on the receiving side. So again, each layer communicates only with its counterpart layer on the other side. But ultimately, at the physical layer, again, as mentioned, you don't see a whole lot of programming or configuration. Everything is very basic, very fundamental. But, of course, it is where really everything actually happens. The only way to get the data from one point to another is for it to cross that physical medium. And it is the responsibility of layer 1, or the physical layer, to handle that portion of the communication. So it is, of course, the beginning of all network communication. Now, in this presentation, we'll take a look at layer 2, or the data link layer. And this is responsible for node-to-node data delivery. Now, what that effectively means is that this is where we start to see the specific identification of a sender and a receiver. The physical layer really is not aware of that. It is just responsible for ones and zeros and handling the transmission of data across the physical media. So layer 2 receives data coming down from the network layer and then passes it on to the physical layer. But during that process, it creates frames and adds physical addresses. Now, very loosely, frames, in essence, identify the beginning and the end of any given transmission, just like a frame around a picture, outlines or borders the picture, if you will. But really, it's the idea of the address that comes into play here. Now, it is known as a physical address, and we'll also see in a moment a term that you might be familiar with, a MAC address, a media access control address. But this is the first instance of any kind of address. There is no addressing at the physical layer. So now that we do see an address appearing, this is how we can define who is the sender, who is the receiver. Now, it also handles error-free transfer, so the other layers can assume error-free transmission over the medium. Now, we've talked already about different types of implementations where acknowledgements are used to say something was wrong with that, please resend it. But this, again, is at a much lower level. So we're talking about ones and zeros, really, at this point, being missed. So the data link layer, in essence, is still responsible for saying something's not right here. This needs to be retransmitted. So it's a very similar process, of course, but just at a more fundamental level. And it does this by implementing what's known as a checksum. So a checksum is a mathematical calculation that is applied to a chunk of data that says, if you have this value and that value, then it should add up to this other value. So this is a very, very loose description, but let's just say you are sending the number 2. Then you can say, well, let's add to that number, and you should get an answer of 4. That's a very simplistic example of a checksum. So if I receive this unit of information, and let's just say one of the values was lost, so I only get 1 as a value, and I'm told to add to that value, I will get an answer of 3. But I'm told the answer is supposed to be 4. Therefore, I can assume I missed a value. I did not get 2. I only got 1. Therefore, something was wrong. So please send another value. Again, a very simple example of a checksum. But then we also see the source and the destination address come into play here, and of course, the data itself. So we're starting to see this definition of format, characteristics of the transmission itself that just don't happen at the physical layer. So there are several other functions happening at this layer. Physical addressing, which we did talk about, and again, that is also known as the MAC address. But frame traffic control, frame sequencing, frame acknowledgement, again, detecting and recovering errors occurring at the physical layer. Frame delimiting, again, identifying the start and the end. And frame error checking, that checksum process. So we're starting to see much more control over the transmission itself, as opposed to just the physical layer where it's just send out a bunch of ones and zeros. We also see establishing and terminating the links, so we know when to open the communication and close it. Media access management, meaning who is actually using the media at this point in time. Flow control, error control, and access control. These are all implemented at the data link layer to just implement some form of management to the communications, because if there's no management, then basically everyone is going to try to access the media at the same time, and there's just no way to control that type of traffic. So the data link layer starts to implement these types of control mechanisms. Now, as the OSI model developed, the data link layer was subsequently divided into 2 sublayers, or subcomponents, if you will. The LLC, which is the logical link control sublayer, and the MAC sublayer, or media access control. So looking first at the LLC, this provides an interface between the media access methods, which are down at the physical, and the network layer protocols, which are above it in layer 3. So it's just a way to pass data from one to the other, but it also determines at this point if the communication is going to be connectionless or connection-oriented. Now, that is essentially at the request of higher level protocols, such as TCP or UDP up in the transport layer, but this is where you see the actual implementation, some of those rules that we defined for connection-oriented communications are implemented by the LLC. The media access control, or the MAC sublayer, is responsible for the connection to the physical media, so actually getting it down to the ones and zeros. But before it does, it applies the MAC address, a 12-digit hexadecimal number, which is unique to every single computer, or more specifically stated, every single network interface in the world. There is never a duplicate of a MAC address. So the LLC, not concerned with the addressing, more so the format, the control mechanisms. The MAC, not concerned with those mechanisms. It's more concerned with the addressing. But both of them put together define the overall data link layer. Now, our next layer is layer 3, or the network layer, and this is responsible for packet addressing, which I'll come back to in a moment because we have touched on addressing already, but more to the point, we see a conversion of addresses happening here, logical to physical. Now, that actually depends on the direction. If you are the sending system, then a packet is traveling down the stack, and a logical network address does get passed to the data link layer, where we find the physical or MAC address. But if you are the receiving side, the packet is traveling up the stack in the opposite direction. So a physical MAC address is then converted to a logical IP address. And therein lies the distinction. Your physical or MAC address is always the same. It never changes. The logical address, the IP address, can be changed at any time. And the IP address resides entirely at the network layer. And if you have ever configured any kind of network interface, you know that you can apply any valid address that you want. If you are in different locations, for example, even a small home network, you might be familiar with the fact that almost all of them use the same 192.168.something.something logical IP address. In other words, many of them are reusable. You can find the exact same address in one network as you might in another, but it's because they are separated. They are different networks that you can reuse those same IP addresses over and over again. So again, logical are a little more flexible. They're reusable and they can be changed. Physical cannot. They will always remain the same. So now we start to see a source to destination delivery, but using a particular method. And in this case, that method is routing. So getting packets from network to network, which is of course absolutely required to use the internet. You would not have to use routing if all of the systems are in the same network. And in fact, you wouldn't even need a logical IP address because the MAC address would be sufficient. Every system within that collection would be able to distinguish each other by their unique MAC addresses. But as soon as you have two separate networks, now you need a way to connect those networks, and that is routing. So routing happens entirely at the network layer, and as such requires a logical IP address to be able to implement routing. So, like all layers, the network layer takes services from the data link layer, the layer below it, and then provides services to the transport layer, the layer above it. And again, this is dependent on the direction. So we're traveling up the stack in this case, but that's fine. It just underscores the idea that any given layer is only aware of the layer above it and the layer below it. That's its whole world. So if we were on the sending side, it would be the exact opposite. It would receive from the transport and send to the data link. But again, it's just the fact that it only knows about those two layers. So in terms of the functions, you see things such as subnet control within any given subnet that is bordered by a router. It can implement controls such as throttling. It can say, hold on a second, I'm too busy here. Things are really filling up in my buffers. I'm accepting too much data. So the other sides need to slow down. Subnet usage accounting can keep track of frames if you are in an environment where billing is an issue based on overall bandwidth usage. You can produce those types of counting invoices to say you used this much in terms of bandwidth. And again, that address mapping, the translation of logical addresses into physical addresses, because they both still need to be known, but the network layer is responsible for applying the logical address. Internetworking, of course, provides the capability for one network to communicate with another one. So it provides that logical connection between different networks. And again, the internet is the best example of that. And we can also combine various networks to form a larger network. Within fairly large environments, they will typically subnet their networks into smaller units, but at the same time, those smaller units combine to form a larger network. So logical addressing, again, combines large number of networks. It allows you to create a very large environment up to the size of the internet, but has to define an addressing scheme to still be able to uniquely identify each device on the internetwork. So again, if you think about the large organization, never mind the internet, you can still define an internetwork if you have, let's say, several physical or geographical locations, one in this city, one in that city, and one in another city. Well, you can connect all three of those and make your own internetwork. So again, you're taking network 1 and combining it with network 2. and combining it with network 3. That is an internetwork, and you need to be able to get between them, and yet you still need to accommodate each individual device on each internetwork section. So you still have to accommodate everyone, and this is where the addressing scheme comes into play. Now, we will talk about that in much greater detail later on as well. We also see packetizing, which creates packets upon receiving data from upper layers. The packets are created by way of encapsulation, which is basically surrounding a packet with more information on either side. It's almost like a packet within a packet. And the IP protocol, which again resides at the network layer, defines the packet format. What is the structure? And of course, the IP address is part of that format. The sending system and the recipient both need to be defined as part of the packet format. Fragmentation is also implemented at this layer, and fragmentation involves dividing larger packets into smaller fragments. In some communications, the packet might simply be too large, so IP will divide it up into smaller units and then identify each one so that can be more easily sent out over the medium. And then because each one is identified, it is able to be reassembled once it has been received, even though it has been fragmented. So ultimately, the network layer is primarily responsible for defining networks. It's not so much concerned with the individual systems within a network, but rather, how do I get data from network A to network B to network C? And again, the other primary component is, of course, the IP address, that logical address that is changeable, is reusable. And those other functions will always be implemented at this layer. But again, as its name indicates, the primary job of the network layer is to define the boundaries of any given network and how to pass data between those networks. Continuing on, our next layer is layer 4, or the transport layer. And here we find the management of end-to-end message delivery from the source right through to the destination, and along the way providing error checking to ensure that there are no duplications or errors during the data transfer, ultimately so that messages arrive intact and in the correct order. Now, as far as the layer itself, it resides at the core of the OSI model, and as packets are traveling up the stack, the transport layer takes its services from the network layer below it and then provides services to the application layers above it. And on the way down, as the packet travels down the stack, one of the primary functions is the segmentation of any given message. It accepts the message from the session layer and, again, passes it to the network layer. But what we see here is the message being divided up into packets. That's one of the primary functions of the transport layer. Now, some other functions include the message acknowledgement and traffic control. Now, that does depend on the protocol that's being used, but when it is being implemented, this is where it happens. We also see what's known as session multiplexing, and this is due to the fact that any one system might be communicating with any number of other systems. So it multiplexes those connections together over one logical link, and it tracks which messages belong to which sessions. And it also implements what's known as service point addressing, when you may still have just two systems, but there can be several applications in use at the same time that are all communicating with that other system. So service point addressing is to ensure that the correct packets arrive not only at the correct system, but are processed by the correct application. Now, we also see flow control implemented here, and we did see this down at the data link layer, but this is renegotiated, if you will, using different protocols, and it prevents the source device from sending the data packets at a faster rate than the destination can handle. We also see error control to ensure that the entire message arrives without error. Now, again, this is where the two transport protocols of TCP and UDP reside. Again, recall that TCP is connection-oriented, UDP is not. So depending on the protocol, you will see one of two things happen. So if you are using TCP, then it is a connection-oriented transmission, and this provides reliable transport of data. The receiving device sends an acknowledgement upon successfully receiving the packet. So we see the sender and the receiver implementing what's known as synchronization, and even that synchronization is acknowledged, meaning they are just setting things up. They are establishing the rules of communication, and they are both agreeing on that. They basically negotiate how the transfer is going to take place. So that's what the synchronizations and the acknowledgements are all about. Once that is complete and both parties agree, then the connection is established. At that point, we can start sending the data. But in a connection-less transmission, something using the UDP protocol, the receiver does not acknowledge the receipt of a packet. The sending device simply assumes the packet arrived successfully. And again, this is not as reliable, but it enables faster communication between the devices. So ultimately, again, it really comes down to what you need. Do you need reliability or do you need speed? And you simply choose the appropriate protocol. But if it is UDP, it will be connectionless, and we can get a little better performance. Perhaps not as reliable, but sometimes you just want the speed. So all of this is happening at the transport layer. And again, ultimately, as its name indicates, it is the actual movement of the data. This is really where you see it getting from point A to point B, and it's just a matter of how that movement takes place. Moving along, our next layer is layer 5, or the session layer, and this is responsible for communication between two devices. And that statement in and of itself might seem somewhat generalized and possibly even redundant, but in this context it refers to the beginning, the maintenance, and the ending of any given communication. So let's go back to layer 4 for a moment, the transport layer. We talked about establishing a connection at this layer. The connection is simply saying, all right, we have connected to each other. But that's just the beginning of the process. Again, think about a phone call. If I pick up the phone and dial your number, and you answer and say hello, there, we have a connection. The session more so refers to the entire conversation. So the beginning is certainly establishing the connection, but maybe at some point during our conversation, one of us will get cut off or will lose signal. Well, we know that somebody should try to call the other person back. That's the maintenance. And then once we have both said goodbye and the conversation is over, we know that we can hang up. We should not just leave the phone sitting there still connected. So that's the ending. So it's the overall communication, all aspects from beginning to end, that represents the session. So this ultimately regulates the flow of data between the two devices much more effectively. Now, the session protocol in use will define various parameters for the connections, but it is charged with managing the transfer of data in terms of who can transfer and for how long. So again, you want to take turns basically, and you generally do not want to leave the connection open once the communication has completed. It should be terminated. So some other functions include the session establishment, the maintenance, and the termination, which again enables the two different machines to establish a session. And we see here session support, which implements security on the session, name recognition of the users and the machines, and things like logging in, so passing credentials back and forth. So those are just all examples of things that should be implemented with a connection. Some sort of negotiation should occur, and once it has all completed, everything should just be shut down. So we see more so just a lot of synchronizations happening back and forth here at the session layer. It's not so much concerned with passing the data, but agreeing on how we will control the passing of that data. And one of those aspects is what's known as dialogue control. This determines which device communicates first and how much data will be sent. Now, with respect to dialogue control, there are three types: simplex, half duplex, and full duplex. Now, simplex is one-way communication, one at a time. You can equate that to two-way radios, walkie-talkies, for example. If I push my button and speak, I cannot listen during that time. And if you are receiving, you cannot speak during that time. When you push your button, it cuts off the receiver. So you can only send or only receive, and it has to be one person at a time. Half duplex is both ways, so bidirectional, but still one at a time. Full duplex is bidirectional, two at a time. Now, again, to imagine that, a phone call kind of borders both of those, if you will. In theory, a phone call is full duplex because we can both speak and listen at the same time. Bidirectional, both of us could speak if we wanted to, but it wouldn't be a very effective communication. I wouldn't understand you, you wouldn't understand me. So again, in theory, it is full duplex because it has that capability, but in practice, half duplex would be a normal phone conversation. I speak, you listen, you speak, I listen, but it is bidirectional. So again, it really comes down to the type of protocol, the type of application, but in terms of network communications, full duplex is certainly the fastest. Both of us can send and receive at the same time. So some other functions include dialogue separation. This adds checkpoints or markers within a message so that we know where the beginning and where the end is, and also where it might need to be resumed from if it was interrupted. Again, that's the maintenance. So some examples of the protocols that operate at the session layer: NetBIOS, named pipes, and RPC. But again, the overall idea of the session layer is just that maintenance, that set of guidelines over the entire communication, so that for the most part, we just know when it starts, how to maintain it, and when it ends. Now, our next layer is layer 6, or the presentation layer, which is often referred to as the translation layer, and I'll come back to that point in a moment. But its primary job is to present data in a uniform format to the application layer, which essentially means it masks any difference in data between two different systems. So coming back to the translation, it formats the data that will be presented to the application layer by translating that data into a common format known to the application layer at the receiving station. So to visualize this, imagine two email applications. I'm just sending you an email, but I'm using email application X and you are using email application Y, and we have them set to use different data formats. Maybe I'm sending out in plain text and you are receiving in HTML. Well, In this case, it is the job of the presentation layer to ensure that the application does not need to concern itself with converting those types of data. The application simply wants to present the data it receives, but it's the presentation layer that is responsible for ensuring the application understands that data and, in essence, just does not have to worry about it. So this is where you see this translation happening. Now that's a fairly simple example. We'll see some additional ones in a moment. But we also see functions of character code translation happening here. ASCII, or American Standard Code for Information Interchange, and what's commonly referred to as EBCDIC, which is Extended Binary Coded Decimal Interchange Code. These essentially are translation methods from binary to character information. They're just different approaches, but of course, binary is at the lowest levels, and character is what we expect to see. It also handles data conversion with respect to the bit order. The CR-CRLF stands for carriage return and carriage return line feed. Carriage return is, of course, the old typewriter when you hit enter and move the carriage back to a starting position. It's understanding and or recognizing where those have happened, and line feed is more or less the same thing for Linux and Unix systems. An integer floating point is recognizing the difference between whole integers, those without decimal places, versus floating points, those that do. So again, we see conversions happening here from binary types of data and or various formats of data into what the application can understand as character-based data that, of course, we ultimately need to understand. So here are two of the most common functions that also occur at the presentation layer, and again, this comes back to the translation. Data compression is heavily used in just about every computing environment, which of course reduces the number of bits that need to be transmitted over the network and or stored on any kind of storage media. But compression is in essence a translation. It uses, in some cases, various sets of characters that represent other sets of characters. So for example, just to use a very simple one, you might use the symbol of the asterisk to represent the word hello. Well, a single character of the asterisk is, of course, much less data than the 5 characters in the word hello. So the data is compressed, but we need to know how to uncompress that data. We need to know the conversion. So again, we translate one character to another. So again, it is the job of the presentation layer to do that. And data encryption is perhaps the best example of all, because encryption, typically the opposite in terms of size when it comes to compression. When you encrypt data, it typically is much larger, but it's much safer because it scrambles characters and uses way more than what are actually required. So the word hello might be represented by a string of characters that makes no sense to us and could be possibly hundreds of characters in length. But that's the idea. We want to favor the security of that, but we still need a way to understand the data. We need to decrypt it. So again, it is the presentation layer where this happens. If the presentation layer didn't exist, we would see a bunch of encrypted data in the application that makes no sense to us. If it was compressed, we'd only see a bunch of meaningless characters. So again, the presentation layer undoes the compression, undoes the encryption, and presents it to the application so that we see normal data. So again, it's something that really is responsible for translation, hence the term. But presentation layer is where this occurs so that the application itself just does not need to concern itself with handling all those different types of possibilities in terms of how the data is represented. All right, our final layer of the OSI model is layer 7, or the application layer. And this serves as the window for users and application processes that need to access other network services. It is the interface between the program and the rest of the protocol stack. So it's appropriately named because as users, we directly interact with an application, but the program itself, the application, doesn't really reside within layer 7. If you will, it would be just above layer 7. That's what we use as users to interact with the system, but it is the protocols within layer 7 that directly support that application and allow it to access the appropriate network services. So, to give you a better idea of what that means, these are some of the network services, and these are just a few of many. But FTP, File Transfer Protocol, DHCP, Dynamic Host Configuration Protocol, DNS, Domain Name System, SMTP, Simple Mail Transfer Protocol, HTTP, Hypertext Transfer Protocol, POP3, Post Office Protocol version 3, and NFS, the Network File System, are all different types of network services. If I want an IP address, I use the DHCP network service to request an IP address. And I can use an interface within my operating system to do so. So there is an application in front of me where I can say, renew this IP address. That is the application, but it is the DHCP protocol that handles the request to get that IP address. A much more familiar example, open up a web browser. The browser itself is the program, and again resides just above layer 7, but if you look at the address, you see more often than not http:// then the name of the website. So that application, the browser, is directly dependent on the HTTP protocol to request the website from whichever server hosts that site. So again, that's the network service, getting the site. The browser is the program. So they entirely depend on each other, but it is the function of these application layer protocols to simply provide the services to the various types of applications that we use. So in terms of the functionality, it allows us, users, to interact with the applications. The application accepts user input and passes data down to the lower layers. Another example of that, using email. I just type in a message into the email interface. The application accepts that and sends it on its way down the stack. So this allows for easier application compatibility and implementation, and I'll clarify that in greater detail in a moment. But essentially, applications do not have to be rewritten for different types of network environments. So if we look at some examples, mail services, something we use every day. Email applications do not need to be consistent to send or receive messages across different environments. I don't need to concern myself with what type of email application you are using if I'm sending you an email. I don't need to concern myself with what type of network environment you are using. It's just a matter of me knowing your address. So I take advantage of the SMTP network service to send that email across the internet, and in essence, you receive it. It doesn't matter which program you are using, nor does it matter what type of network environment you are in. File transfer, access and management, or FTAM. Multiple types of FTAM applications can be used to access and modify files remotely. FTP is a good example of that. If I'm a web developer, there's a very good chance that I develop my websites locally and I transfer the files up to a server. So again, there are many different types of applications, and I don't need to concern myself with which one should I use? As long as it supports the FTP protocol, then I can use that application. And of course, browsers. This provides internet access for all types of networking environments. And as a developer, I don't need to create a browser for network environment A or network environment B. As long as the HTTP protocol can be accessed, that is really all I need to concern myself with. So that's where that compatibility and easier implementation comes into effect. I just don't need to concern myself with the lower layer protocols as an application layer developer. As long as I use those standard protocols, then my application will work. So that's where you see that easier implementation. The compatibility just really is not a concern. As long as it's compatible with the application layer protocols, yes, that's a concern, but that is really as far as I need to go. I don't need to make different applications for different types of network interface adapters way down at the physical layer, or a different browser, one for the TCP protocol and one for the UDP protocol. As long as it can just access its immediate layer below the application, that's it. Everything else is up to the lower layers, and compatibility and integration and implementation becomes much easier to facilitate. All right, time for another exercise, and this time we'll ask you to describe the physical layer, the data link layer, the network layer, the transport layer, the session layer, the presentation layer, and finally the application layer. So again, what we'd like you to do is take a few minutes, pause the video, and jot down some responses. Then we'll come back in a few minutes to see how you made out. So we'll see you shortly. All right, so our task was to summarize each layer of the OSI model. So we'll begin at the top. The application layer accepts data from the users. It is essentially our interface, and it provides us access to the various protocols and network services that we need to communicate. Data is then passed to the presentation layer. It handles the format of the data. Features such as encryption and compression are implemented here. The session layer manages the overall communication from endpoint to endpoint and from beginning to end, so the rules of communication. The transport layer handles the delivery method, either using acknowledged guaranteed communications or connectionless non-guaranteed communications. One is more reliable, but the other is faster. At the network layer, we see logical addressing and routing taking place. This is where we see IP, for example. Then the data link layer provides access to the media, physical addressing, or the MAC address. And finally, down at the physical layer, we find hardware, the transmission of digital bits across the media, and then it is delivered to the other side, again, wherein the recipient will receive the packets and they will travel up the stack. And each layer will simply undo what the corresponding layer on the sending side did, so that by the time it is presented to the application, we see the exact same data that was sent. So hopefully you made out okay with that exercise, and if so, we are ready to move on to our next course.